Let's look at this first problem. First problem is could you guys hear me before? My volume was kind of doing weird things. Okay, I think we're good. A rancher wants to build an enclosure for his animals. The fencing material for 3 of the sides. So we want to build an enclosure. And although the problem does not state it, it is going to be a rectangle. Where the materials for 3 of the sides cost $2 per foot. And the material for the 4th side costs $1 per foot. If the rancher can only afford to pay $500, so our budget is $500, what dimensions, oh, it does say rectangle at the end. What dimensions should the rectangle be to maximize the total area? So what dimensions maximize area? So it's good to draw a picture. And I'm going to try and draw my picture the same way that it's actually drawn in the notes. So let me take a look here. So I'm going to draw a rectangle. Maybe it's long and skinny like this. Not the best rectangle I've ever drawn. So let's say this is X, this is X, this is Y, this is Y. You can use any variables you want to label. X and Y are pretty typical choices. And so first I'm going to write down, what do I want to maximize? I want to maximize area. So I need an equation for the area. Rectangle is pretty straightforward. Area is x times y, or base times height, or length times width, or thing times thing. And as you probably have kind of gotten to realize by now, right, when we have a function or a thing we want to maximize that has 2 different variables in it, we really need to have just one variable, because we want to be able to write this so it looks like a parabola, so that we can find the vertex and we can see where the maximal value of the function is. So we need a constraint. And here, the constraint is that we only have $500 to spend. Right? Our constraint is budget $500. But we need to take that constraint and actually make an equation out of it, right? We need to be able to do something so we can solve for X or Y and put it back into the other equation. So we have to kind of decide which sides cost which. I think, let me do it this way. Yeah, sure. So I'm going to say that it doesn't really, yeah, the 4th side is $1 per foot. I know I wrote that kind of a little bit sloppily there. So let's say that this is the side that's $1 per foot. And the other 3 sides are the sides that are $2 per foot. So now we want to write an equation for what the cost is going to be based on the dimensions. So the cost is going to be $2 per foot times X feet plus $2 per foot times Y feet plus $2 per foot times X feet plus $1 per foot times Y feet. And we know that we only have $500 to spend. So we're going to set this equation for the cost equal to the amount of money we have. Because we're going to spend it all. We're going to make the biggest area possible. And then we're going to simplify. One thing I'm going to do is I'm going to drop the dollar signs, but we don't really need the dollar signs to solve this equation or to isolate a variable. So I'm going to say I have a 2x plus another 2x is going to be a 4x. And then 2y plus 1y is 3y. equal to 500. And now I can isolate either variable. It really doesn't matter. I tend to like isolating y because we're kind of used to working with functions of x. So we can isolate y. So 3y is equal to 500 minus 4x, and then divide everything by 3. So that y is equal to 500 thirds minus 4 thirds x. And I definitely want to leave it as a fraction, right? I don't want to use a decimal approximation. I just want to leave it as 500 thirds minus 4 thirds x. Okay, and this is what's going to go back in to my area equation. So that now I can rewrite the area as x times this expression for y, which is 500 thirds minus 4 thirds x. I'm going to go to the other side. So we need that. So we have that the area is equal to x times 500 thirds minus 4 thirds x. And we're trying to find the dimensions, that is the values of x and y, that maximize the area. So we want to find x and y that maximize area. So of course, we're going to find the x coordinate of the vertex. So I'm going to rewrite this. This is going to be area equal to 500 thirds x minus 4 thirds x squared. I'm going to distribute that. And then I'm going to rewrite this just so it looks more like the standard way of writing a quadratic. I'm going to write area equals negative 4 thirds x squared plus 500 thirds x. So it's more clear that my b value is 500 thirds and my a value is negative 4 thirds. It's not necessary to do this if you know what's what. It's just nice to kind of see things in the standard way. So I'm going to find the x coordinate of the vertex. The x coordinate of the vertex is going to be negative b over 2a, which is going to be negative 500 thirds over 2 times negative 4 thirds. And I'm going to simplify this. So this is going to be negative 500 thirds divided by 2 times negative 4 thirds is negative 8 thirds. I can get rid of the negatives. And when you divide fractions, you really going to flip and multiply by the bottom. So this is going to be 500 thirds times 3/8. The 3's cancel. You get 500 divided by 8. And we can reduce that fraction to 250 over 4 or 125 over 2. Or if you prefer, 62.5. So that's the value that x is that's going to maximize the area that we can get with how the sides cost. So x is going to be 62.5 feet, or 125 over 2 feet. We could find the y coordinate of the vertex, or I should say the a coordinate of the vertex, right? If I wanted to, I could find the a by plugging in this value here. I'm not going to actually do it. I just want to show you that if I did it right, I would probably plug it in here actually and get x, which is 125 over 2 times 500 thirds minus 4 thirds times 125 over 2. And this would equal whatever the maximum area is. But again, the problem didn't actually ask us to find the maximum area. So we are, not that it's not good to know this, but we're wasting our time if we're only trying to answer the question. So we found x, but we were asked to find both dimensions x and y. So we need to go back and figure out what y is. Now, this is usually going to be found by seeing where you solve for y in your constraint. So if I found X and I still want to find Y, look at your constraint and see how you isolated Y. Oh, look, we exactly have an equation for Y in terms of X. It's 500 thirds minus 4 thirds X. So I'm just going to use that equation to find the Y value. Let's do it up here. Not surprisingly, this is X times Y, so we can see, oh yeah, that's the Y value. So Y is going to be 500 thirds minus 4 thirds times 125 over 2. Let's see, we can cancel a little bit. We can cancel a 2 here and a 2 here to get 500 thirds minus 2 times 125 is 250. 3 times 1 is 3. So 500 thirds minus 250 thirds is 250 thirds. So Y is 250 thirds. You could also say it's, although it's not less nice as a decimal here, Y is 83.33 continuous. That would be a fine way as a decimal to write it as well. So these are the values of X and Y that maximize the area while still only spending $500. Okay, so any questions? Oh, does the labeling matter? That's an excellent question, Jonathan. I want to say yes and no. The general answer is not really. The labeling doesn't matter. So you could have totally labeled it so that, you know, these were X's and these were Y's, or you could have labeled it so the X one was $1 a foot and the Y's were both $2 a foot. Here's what will happen though. Like if you specifically, if we changed which side was the dollar per foot side. So if the X's were the side that cost $1 per foot and $2 per foot, and the Y's are both $2 per foot, we would get then the results being changed, meaning we would have ended up getting that X was equal to 83.33 continuous feet, and that Y was equal to 62.5 feet. So that's the difference. If you try to change the labeling, the results will change correspondingly. But that's about it. Other questions about this? Checking, make sure my volume's on. So I know I said this a lot last class. I'm going to say a lot this class. In fact, actually, I do want to point. No, I don't want to point out. So I'll just point out here. That if I were to graph this area as a function of X, the x-intercept would be 0 and 125. And the vertex here would be where X is 62.5, and the Y value would be your maximum area. I suppose you could say it's your A value. Right? It's the A coordinate of your vertex. And so just the reason I'm saying this is because I've definitely seen in the past a lot of people get confused and be like, oh, that's my Y value. That's the thing that should be like the Y here, which it isn't. Right? The Y here ended up being 250 thirds or 83.3333. Whereas this value here we would get by actually plugging 62.5. It would be much larger. This value here is actually equal to the X coordinate we found times the Y coordinate we found. Or 125 over 2 times 250 over 3. That's what that maximum area would be, which makes sense, right? The area is just X times Y. Okay, so yeah. And then I should also mention, just because it's kind of interesting to see, these other points on the parabola, like maybe this is, X equal to 40. This would be a different place where we would get some X and Y values, but the vertex here wouldn't be met, or we wouldn't get the vertex, right? We'd have some other area that's not the maximal amount of area. So that's why we're looking for that point there, because that's the point that's going to maximize the area. All right. Also, hopefully everybody saw that I graded the homework on Gradescope, and you should be able to, like, for any place where you missed points, there should be like a grading thing that you can see why you missed points or you missed points. But if you ever have any questions about the homework, please don't hesitate to ask. I'm happy to talk about why something was graded a certain way, but I will just point out, do look at Gradescope to see if you can find out why before you ask me. You're always welcome to ask me though. What did the second x-intercept say? The one I just erased, or this one here? Is that what you're asking about, Jonathan? Okay, are you asking about this point here?
I'm asking about the x-intercept, the one, I think it says 125. Is that what it says?
So this one, are you talking about over like this 125 over 2?
It's like on the graph, but it's like 40 and
the intercept, sure. Yeah, this is the x-intercept.
Does that say 125?
Yes.
Okay.
And so you're right though. I didn't talk about that. The reason I know that the x-intercept is 125 is actually kind of for two reasons. One, I know the vertex is always halfway between the x-intercepts, and one of the x-intercepts is 0, so the other one has to be 125. The other way I know, and I think I did erase my picture here. The other way I know it's 125 is that the x sides cost $2 per foot. So if x was 125 feet, this side would cost $250, and this side would cost $250, which would totally exhaust the $500 of budget I have. So 125 feet for x would mean that y was 0. And so that's why we would get 0 area. So that's how I know, another way I know that 125 is my x-intercept. It's not really, so I should say, for these optimization problems, you do not have to be able to graph this parabola at all. But I really want to kind of make the connection for you that this parabola, right, if the x-axis is the length of the side x and the y-axis is how much area there is, this parabola is representing what your x value and your corresponding area value are. And so we're looking for this point. We're looking for specifically the x value, which is 62.5, because that's going to maximize the y coordinate, which is the a coordinate, which is the area. Okay. So let's look at the next one. Hopefully you guys are having an all right Wednesday. So the next question says the following. Find two numbers whose sum is 1 and the sum of the squares of the numbers is minimized. They even tell us the thing we're trying to maximize, or sorry, minimize here. They say that the sum of the squares is given by SS for sum of squares equal to x squared plus y squared. And again, we want to minimize this. Okay, same kind of deal. We have the thing we want to maximize or minimize, in this case, minimize. We need to find a constraint. One thing I've noticed about these optimization problems in general is that you're almost, not always, but most of the time there's going to be two equations. One equation is the thing you're trying to optimize, and that's never actually going to be equal to a number, right? It's just going to be name of the thing equal to what it is in terms of the variables, and that's it. And we're trying to make this as big as possible. So since we don't know what makes it as big as possible, it wouldn't make sense for it to equal a number. whereas the constraint almost always is some other equation where it is going to equal a number because we are limited by that equation. So here, if I read this thing, I see I have two numbers whose sum is 1. So that means the numbers x and y have to add up to 1. So that's our constraint, right? We've got some equation and it's equal to a number. In this case, the number is 1. All right. So just like before, we're going to take this equation, we're going to solve it for one of our variables, and then we're going to jam that into the thing we're trying to optimize so that we have something that looks like a parabola. Eventually in your calculus class, you will optimize things that are not parabolas, but that is later. So I'm going to actually solve for x, even though I usually solve for y. So let's solve for x. So I'm going to get x equal to 1 minus y. And then I'm going to substitute that back in to the thing we're trying to optimize. So this equation is going to become that the sum of the squares is equal to 1 minus y quantity squared plus y squared, which I know is quadratic, but I need to simplify it so that I can actually find the vertex of it. So this is going to be, let's see, if I multiply this out, 1 minus y squared is 1 minus y times 1 minus y. And it's going to give me 1 minus y minus another y is minus 2y. And then minus y times minus y is plus y squared. And then plus another y squared. So my equation looks like the sum of squares is y squared plus y squared is 2y squared minus 2y plus 1. So that's the thing I'm trying to maximize. And so I feel like I often make a mistake in these problems. I guess I just didn't write it as well as was written here. The question really said, find two numbers whose sum is 1 and the sum of the squares is minimized. So we're looking for x and y. So I will try my best to make sure that it is clear what we're actually being asked to find. Because sometimes I will admit I do a bad job of asking what we're looking for. All right, so let's go ahead and write this on the other side because I feel like I want to draw some pictures. So I've got that the sum of the squares is 2y squared, right? That's right. Minus 2y plus 1. I think this pen is done. All right, and I'm trying to minimize this. All right, so I'm trying to find the vertex of the parabola. And so this is where I feel like the notation can be a little confusing. I'm going to find the negative b over 2a. But since this is my output and the y's are my input, I'm kind of thinking of the vertex. If I'm going to use the notation that I usually use, okay, this pen is awesome. Just throwing away pens. The vertex, I'm thinking of the x coordinate as, or I should say really the first coordinate as Vy, and the second coordinate as VSS. Right, so don't let the x's and y's confuse you, but here we're thinking that Vy is negative b over 2a, because right, our function's in terms of y. So that's going to be negative 2 over 2 times 2, which is 2 over 4, which is 1/2. So the y coordinate's 1/2. And it looks something like this. Haha. Right, so there's my vertex. at 1/2 comma whatever the sum of the squares value is, which we could find, right? We could totally plug in 1/2 here for y. You get the sum of squares is 2 times 1/2 squared minus 2 times 1/2 plus 1, which is 2 times 1/4 minus 2 times 1/2 is 1 plus 1. Those cancel out. And I get 2 times 1/4, which is 1/2, which is kind of interesting. So I will point out that this question might be slightly misleading. So the y value is 1/2. The sum of the squares is also 1/2. And it's also going to be interesting that if we go back and we actually find the x value is also 1/2. Kind of weird, but it does make sense, right? 1/2 squared is 1/4, plus 1/2 squared is 1/4, and 1/4 plus 1/4 is 1/2. So here, all the things are 1/2, both the dimensions, the x and the y, as well as the thing that we maximized, which is the 1/2, 1/4 plus 1/4, which is 1/2. So it's a little bit weird, but perfectly okay. I kind of feel like we should do one more of those because I feel like that one's kind of wonky. So let me grab another one here. I'm gonna go off notes for just 1 second. Sure, gotta close that. So let's look at another example. Sure. So let's say we have two numbers whose sum is 6. And I want to minimize the sum of the square of the first number and 3 times the sum, 3 times the square of the second number. So here's what we're trying to minimize. We're trying to minimize this sum. I'll just call it a sum. It's the sum of the square of the first number plus 3 times the square of the second number. Okay, and then I have a constraint. What's my constraint? Oh, excuse me. What is my constraint in this problem? What's the equation that we have to have here if our numbers are x and y?
It has to equal 6.
I'm going to ask a follow-up question, Aaron, and anyone can answer. What has to equal 6?
The sum of x squared. Oh, of that equation.
So this equation is the one we're trying to minimize. And typically the thing we're trying to optimize doesn't end up equaling a number until after we've done kind of the process. So we kind of have to go back and, so you're right that something has to equal 6. But and I might have used some bad language here. So this says two numbers whose sum is 6, meaning not the sum of their squares or 3 times the square, but just the numbers themselves. So I'm looking for exactly what someone just wrote, x plus y equals 6. But you're right, I did kind of use the word sum in 2 different places, right? I said sum here, I also said sum here. So maybe I should call this the sum of the squares, even though it's a little bit more complicated than that. So then I'm gonna do the same thing I did last time. I'm gonna isolate one of these variables, I'm gonna throw it in there. And since this part is slightly more complicated, I'm actually gonna isolate x over here so I can plug in for x here, because it's just a little bit less work that way. So I'm gonna find that x equals 6 minus y. And then I'm going to plug that into x here. So the sum of my squares is equal to 6 minus y squared plus 3y squared. And now, if I multiply this out, I get 36 minus 12y plus y squared plus 3y squared. Or simplifying and writing in the usual order, 4y squared minus 12y plus 36. The y coordinate of my vertex, which is the input, right? I know, again, it's kind of strange, but right, the y's are the inputs here because that's the variable we're working with, is going to be our negative b over 2a, which is going to be, let's see, negative 12 over 2 times 4, which I can cancel a 4 and a 4 and get 3 halves. I don't really need to find what the sum of the squares is. Instead, I'm just going to go back and say, okay, if y is 3 halves, x is going to be 6 minus 3 halves, which is 12 halves minus 3 halves, which is 9 halves. You could say that this is 1.5 if you prefer. You can say that this is 4.5. So those are the values that would maximize this sum of squares. And not that we were asked, or sorry, minimize. I said maximize. I meant to say minimize. Sorry. Not that we've been asked, but we could actually find what the minimum value is, right? We could say, okay, if I plug in x equal to 3 halves, sorry, 9 halves, and y equal to 3 halves, I get 9 halves squared, which is 81 fourths, plus 3 times 3 halves squared, which is 9 fourths. 3 times 9 is 27. So I get 81 fourths plus 27 fourths, which turns out to be 108 fourths, which reduces to 54 over 2, which is 27. So if I were going to graph this, if I was going to graph this parabola, it would look something like this, where the minimum value was at y equal to 3 halves, and the sum of the squares, which is on the y-axis, equal to 27. So that's a little bit better example of what I was trying to say before, right? That this, in this example, in the previous example, the y variable is acting like your input, which is what we usually think of as x. And the sum of squares is acting as our y variable or our output. Just trying to help you avoid any confusion in the future. So generally the process, find the thing you're looking for, right? Find the quote unquote x coordinate of the vertex, or the input coordinate of the vertex, and then use that, which in this case was 3 halves, to find the other thing you're looking for, which was x. All right. So let's go ahead and look at, there's a couple more problems on the notes. Let's grab that, sure, where'd you go? Here's another distance one. I think distance ones are important. They actually do come up a lot. So I want to find the point on the graph of y equal to the square root of x. That is closest to 8, 0. Okay. And we don't actually have to draw a picture, but I think it's always a good idea to draw a picture. So my square root function looks like this. Right? It has the point 1, 1, and 4, 2, and 9, 3, So we're looking at this point here, 8, 0. And we're asking ourselves, what point on this function, I'll write about there, what point is closest to 8, 0? In other words, we want to minimize the distance between these 2 points. So I need to write the distance. So the distance is equal to the square root of x minus 8 quantity squared plus y minus 0 quantity squared. 2 things. Thing 1, if you want to make the distance as small as possible, our job is really just to make the inside as small as possible, right? Because if you make the inside as small as possible, then you'll make the square root of that as small as possible. So what I'm really saying, and which you'll see people do in kind of any class when you have to minimize something that has a square root, is instead of minimizing the distance, we're going to minimize the distance squared, which is just the inside parts. And I'm going to simplify that as just y squared, because y minus 0 is y. The second thing, let me scooch this over just a little bit. The second thing is that, again, we're trying to minimize something. There's an x and a y. We would like there to just be one variable. And we're going to do that by using the fact that this point, x comma y, is on this square root function whose equation is y equals the square root of x. So this point here is really the point x comma square root of x, so that we can replace y with the square root of x. So that d squared is actually equal to x minus 8 squared plus the square root of x squared. I know I didn't really say anything about this here, but in these kinds of problems where you're trying to minimize the distance between like a point and a function, the fact that this other point has to be on the function is your constraint. Right? You're constrained by, oh yeah, this point has to be somewhere on this graph. So this is our constraint right here. And now we've got, well, I should simplify it a little bit. My distance squared is equal to, I'm going to multiply that out, x squared minus 16x plus 64. I'm foiling it out. I'm getting x times x, I'm getting x times negative 8, I'm getting negative 8 times x, and negative 8 times negative 8. And then square root of x squared is just x. So I can simplify this as x squared, negative 16 plus 1 is negative 15x plus 64. And now we can find the vertex. The x coordinate of the vertex would be negative 15 over 2 times 1, which is 15 over 2. Or if you prefer, 7.5. I'm fine with decimals as long as they're like nice ones, but when they're like ones that repeat infinitely, I mean, you can write it like that if you really want to, as long as you write the little bar over it. But like, I like fractions. Fractions are great. Fractions are our friends. I think you guys should like fractions too. Everyone should like fractions. So let's just answer the question. Let's not do any of the extra work. So the question was to find the point on the graph that was closest to 8, 0. I found the x coordinate of that point, right? It's 7.5. And now I want to find the y coordinate. So I'm going to take my constraint, which is y equal to the square root of x, and just plug in x. So x is 15 halves. Y is going to be the square root of 15 halves. So x is 15 halves. Y is the square root of x. So y is the square root of 15 halves, which doesn't really simplify at all. It just is the square root of 15 halves. So our point is 15 halves, comma, square root of 15 halves. Or you could write it as 7.5 comma square root of 7.5. But that is the point on this graph that is closest to that point there. And again, that's because we found the point that minimizes this value here, right? If x is 15 halves, this parabola is going to be at its vertex. And since it's an upward opening parabola, it's going to be minimized. All right, we're out of time. So I will say